Hi, I'm Weina Jin from Simon Fraser University. Today, let's dive into the topic of explainable AI. In particular, we'll review some of the post-hoc explanation methods. So this is offline. We'll first get the motivation of why we will study the explainable AI, then get to know each of the method using gradient-based or perturbation-based approaches. And then we'll zoom out to look at the landscape of explainable AI. So let's get started. So what is explainable AI, or we usually call it explainable AI or interpretable machine learning? So this is the Euro AI paradigm, given some input, and AI will output some predictions. But say in some clinical settings, in those high-stakes decision domains, the doctors will not be satisfied with only a suggestion from AI, because the doctor will deal this patient with some life or death decisions. And doctor may further ask AI, how do you get this prediction? And explainable AI is trying to explain how AI makes such predictions in human understandable ways. So say this is a popular ways of explaining with AI explanation. So we can show the important features on this input MRI to show here AI look at the tumor site, and based on those image features, AI concludes this is a high-grade brain tumor. So this is one form of explanation. And we can hypothesize maybe after this, the doctor will more likely to take the AI suggestions based on their prior knowledge, and may also can easily identify some potential errors if there's some problem with their explanations. So explanation or explainable AI is usually used in those critical decision-making scenario, like in the healthcare domain or finance domain, like in those decisions related to human life or like money, career, etc. And AI need to explain, back up this decision with some rationales to let human know why I make this decision. So that's why we want to make AI more explainable. And explainable AI has those utilities like helping human users to calibrate their trust towards the AI prediction, and also can help a human user to verify the AI decision, or even help users to improve their own problem-solving skills or make some scientific discoveries. So explanation is useful, but opening the black box of the deep neural network is quite challenging, because deep neural network, the state-of-the-art model, usually consists of like millions of parameters with tens of hundreds of layers, and including like some very complex nonlinear mapping from the input to output mapping. So the decision process is very complex for even like human AI developer could not understand. So generally, there are two approaches to open the black box of AI. So first is to, for the already trained model, we can use some post-hoc method, like we will look into in detail today, like gradient-based or perturbation-based method. And the other is train the deep neural network from scratch with some special designed architecture or loss function to make the deep neural network more interpretable, inherently interpretable. But we need to train those models from scratch. So today we'll mainly look at the first approach, which is very easy to use in the popular API, and it can explain already trained deep neural network. So and today we'll look at the most common way of explanation using the feature attribution. So basically, the explanation highlights the important features for the prediction. And the high level idea is because this the decision space is high dimensional, we try to simplify this high dimensional decision space into some low dimensional feature space. So we pick up the important features, and we try to construct some linear function to explain the original nonlinear decision boundary or decision a decision function here. Like here, we show this polynomial curve to mimic the DNA decision boundary. And here we just explain using some tangent line, some linear function around this query input. So that's the high level idea of how we can open the black box of DNA and explain these decisions. So the explanation try to answer this question: how important is a feature to a prediction? So to do so, like here, we can construct some linear function, and we can just simply use the weights of the linear function as explanation. And this is basically the first approach using some gradient-based approach. And the other approach is using some perturbation-based approach, namely to perturb the input and get some output. And based on the input-output pairs, to try to understand the behavior of the model. So let's first look at the gradient-based one. And here is some like results from those different methods we'll look at. And this is based on the same model for the same input. And it kind of generates some similar looking explanations, but some kind of vary from each other. So let's look at each of the methods. For the gradient-based method, we have those like 10 methods to look at. So for the vanilla gradient, it's kind of just use this linear function, this tangent line, to approximate the function around this input x equals I, and use this slope, this weights as the explanation here shown in this heat map. So it's for the gradient signal, it's very easy to calculate. Like you just run a back propagation and you can get the gradient signal for each of the input features, and you can visualize using some visualization heat map here, and to kind of highlight the important region for the prediction. So it's very straightforward using the gradient method. But it has some problem with this simple approach. So the first problem is it's kind of noisy. Here I use some smoothing method, but it kind of still looks like the highlight area is scattered around everywhere and has some high frequency signals. So there are some methods to try to improve this overcome this noisy problem, because the gradient signal is trying to get unstable around the local region. It's quite sensitive. And the second problem is saturation. Like for some flat area, the gradient signal is almost zero, so it cannot signify any important features. So there are other approaches try to overcome the saturation problem as well. So let's look at how different methods try to overcome the noisy problem of the gradient. So one straightforward idea of to reduce the noise signal in the gradient is to modify the backpropagation calculation. So recall in the vanilla backpropagation, we set the negative inputs as zero. So in contrast, in the proposed method called deconvolution, this sets the negative gradient as zero during the backward pass. And you can see from this is the original gradient explanation. This is generated using the deconvolution. It's kind of less noisy. And another a further approach is to combine the two ideas together to set both the negative input as zero and as well as the negative gradient to zero. This is called backprop. So you can see this the heat map explanation generated from the backprop, guided backprop, is kind of much cleaner and easier for our humans to interpret. So those are the methods to modify the backpropagation rules to generate less noisy heat map gradient-based explanation. So another line is to try to visualize the internal activation of the deep neural network, especially for the convolutional layer. For each of the activation map, we can stack them together and visualize to show the localized important region for the final decision. So this is the idea called class activation mapping, or CAM. So the way they do it is very straightforward. They just aggregate the different channels of the activation map together, weighted by the weights from this convolution layer to the final prediction layer. And they aggregate together to get one single heat map explanation. This is called CAM. So grad CAM is quite similar. It's just to replace the weights with the gradient signal. So all the calculations similar, they just replace the weights with the gradient. This is called grad CAM. And guided grad CAM is kind of combine the grad CAM approach with the previously mentioned the guided backprop. They just combine the two signals together to get a much cleaner, nice looking explanation here. So that's another branch to visualize the internal activation map of those CNN models. And another idea to reduce the noise of the gradient is to, it's called smooth grad. In the title, they call removing noise by adding noise. So the way they add noise is to add some noise around this input image and get for each of the perturbed image, they get the gradient of that input and aggregate those gradients together so that to make the gradient more smoother and less sensitive to the input perturbation. So this is called smooth gradient method. So now we look at different methods to try to reduce the noise by revising the backpropagation rules or do some averaging approaches or try to visualize the internal activation map. So next, let's look at the other problem the literature tried to overcome. It's called gradient saturation problem. So the gradient saturation problem is that given some input, we want to get the gradient for the function f. But here, for the given point, the gradient is kind of 0. So it cannot signify any important image input features for the prediction. So the way to do so is we try to select some baseline. Here we use the x equals 0 as the baseline, and we try to generate some explanation using the difference between the function at x equals 2 minus the function at x equals the baseline. So using this difference to attribute the important features to the input feature space. So how do we do so? We have different approaches. So in the first approach, it's kind of vanilla one called input times gradient. So the idea is kind of follow the gradient approach. So we still approximate the complex model with some linear function using the first order Taylor approximation. And for this function, we get the value at x equals I, the input, and x equals the baseline. Here we use 0. And we just calculate the difference. And we use this difference as an explanation. So equivalent equals to the gradient times input. So it's very straightforward and very quick to calculate, but there's a problem because we use the linear approximation for the original function. And you can see when the approximation is not near the local point, like here for the baseline point 0, the approximation value is kind of far from the original function value. So this may not be a faithful explanation to the original function. So to overcome this problem, there's another method called integrated gradient. So the way they do so is kind of, they aggregate all the gradient from f equals f0 to fi. And they aggregate by doing the integral along this path from x equals 0 to x equals I. And so they aggregate all the gradient together to approximate the function difference between I and fi and f0. So this is called integrated gradient. But you can see, because here it's doing multiple calculation along this path from 0 to I, so it has multiple backpropagation. So it's kind of computational intensive to calculate the integrated gradient. And another idea to try to overcome the saturation is also to incorporate the baseline, the delta x idea into the backpropagation to modify the backpropagation. So recall in the vanilla backpropagation, it's kind of the gradient is kind of the infinitesimal change. So the deep-lift method tried to modify the backpropagation to reflect the finite change from the previous neuron to the delta x. So they call it a new multiplier m, and they also kind of devise some calculation to make it the multiplier m can also be calculated using the chain rule. So this is a deep-lift idea. From the high level, they try to incorporate the baseline into the backpropagation calculation. Yeah, so here we look at the different method in the gradient-based method. They try to overcome the problem of the vanilla gradient to be less noisy, or to overcome the saturation problem. So next, we look at another line of approach using some perturbation-based method. So for the perturbation-based method, it's kind of, they perturb the input and collect some input-output pairs. So the one straightforward idea is I just use some sliding window approach, and I occlude part of the input, and I see how the output or the performance changes. So say if an input is very important for the prediction, then the performance will change dramatically. So in this way, we can identify the important features for the prediction. So we just do this sliding window approach and aggregate all the changes of the y, and we can, using this value, to get like explanation. So this is equivalent to getting a feature's marginal contribution. This is called occlusion. Another line of work is called align, local interpretable model-agnostic explanation. So the idea is also to perturb the input. And here you can see this is the input image. We want to know why the model makes this prediction for this input. And to do so, we can sample around its neighborhood and sample different pairs of images. And then based on those samples, we can construct some interpretable models. Here, they also use this linear function to classify the two groups of samples, and use this interpretable model to explain the original complex model. So this is a line method. So it kind of sample around the local neighborhood and construct some interpretable model to explain the original complex function. So we look at the gradient-based method and some of perturbation-based methods, but those methods were mainly heuristically chosen or proposed. So their correctness of explanation is not quite guaranteed. So is there any method that is axiomatic? It turns out Shapley value is such method. So a Shapley value aims to solve the problem. So in a multiple gameplay, including different combination of players, and the different gameplay has different gain, like the money. So Shapley value want to study, find the solution to fairly contribute the total game gain to each of the game player. So it turns out this is formula to this solely a fair attribution to each of the player. And it fulfills those nice property like linearity or efficiency. And it quite fit for this explanation problem. Here we want to attribute each of the image features to fairly attribute their importance to the final prediction. So to calculate the Shapley value, we need to get the different combination of the feature combination and the total and their each individual gain of the game. And in this we calculate the features marginal contribution. And we weighted by the probability of such contribution to get the features contribution to the total game gain. So it's also very straightforward to compute, but for the large dimensional of input feature space like image features, it's quite complex. It's quite computational intensive to calculate the attribution of each image features contribution. So there are some efficient methods to do sampling to approximate the Shapley value methods. So this is the Shapley value or Shapley value sampling method. And another way along the Shapley value idea is called SHAP, Shapley additive explanations. So the idea is to try to propose a unified framework to unify the different methods we have seen, like the lime or deep lift. So we try to use those different methods to approximate the Shapley value. Like linear kernel SHAP is try to estimate the Shapley value using the linear regression method in the line. And the deep SHAP is try to approximate the Shapley value using this backpropagation modification similar to the deep lift. So you can regard SHAP as a uniform method and include different methods to calculate or estimate the Shapley value using some fast approximation like linear regression or backpropagation. So now we look at the specific methods which belongs to the gradient-based approaches or perturbation-based approaches. Now, next, we just zoom out to look at the landscape of explainable AI. So those methods we look at belongs to the feature attribution using the important features as explanation. So there are other ways to explain the model decision, like using similar examples, prototype examples, or counterfactual examples, or using some rules to explain the decision. And the method we look at the meaning-based belongs to the post-hoc approach to explain a already trained black box models. So if we look at those taxonomy, we can compare different methods here in this table for the gradient-based approach and perturbation-based approaches. So gradient-based approach, it depends on the specific architecture of the model architecture. So it's called model-specific methods. So require it to need to be a deep neural network or a differentiable models. So for the perturbation-based method, it can explain, basically can explain any black box model. So it's a model-agnostic method. And gradient-based method, as we see, we need to do the backpropagation. We need to get access to the model parameters. Whereas for the perturbation-based method, sometimes we don't need to get to know any details of the internal parameters of the black box models. So that may be an advantage in some privacy-sensitive applications. And for the computational efficiency, the gradient-based method is usually very fast to compute, whereas the perturbation-based, because it needs multiple sampling, so it's usually very slow. So yeah, so and here I list some software for us to use. We can, based on whether you are using TensorFlow or PyTorch, there are different libraries. You can just either use the library to get the explanation for your model. So yeah, that's all. So feel free to email me if you have any questions or comments. Thank you very much.